So, this is the relation between the output discrete values to input discrete values. Now, I can write down what is the network of consisting of adders and delay element, right, to get this equation. And that black box, if you put in there, you will be able to get the spectrum you are looking for, provided you drive it with a white noise source with a spectral height equal to unity. Now, going back to this white noise, if Sx omega is equal to 1, then we said Sx Rxx tau Rxx n or m is equal to delta n. What does this mean? What does the statement mean? Only when n is equal to 0, there is a correlation between the two random variables taken out of this process at time is equal to n and time is equal to n again. If there is any difference between the time instance of the two random variables you have chosen, even a one delay, they are absolutely uncorrelated. Are you with me or not with this statement? Because what is RxM? RxM is equal to correlation function of two random variables separated at a distance equal to m units. And it has only value when m is equal to 0. That means only those random variables which are separated by 0 distance, that means same random variable has a autocorrelation value, but any two random variables you take with even if 1 unit delay, they are absolutely uncorrelated. So, what all I am asking for is a set of numbers here which are absolutely having a 0 correlation even for one shift. So, such is the set of numbers that you need to generate to feed to the input of this black box. And the computer people have some program which you can pull out the program and say white noise sequence. They generate this white noise sequence which is having this property, not obviously property for all possible values of n, but sufficiently large number of, and you cannot have a white noise spectrum. So, for sufficiently large value of n, they are uncorrelated. And how they write that program? Because after all, program has to be based on some theory. This we will come to know when we come to the next chapter, how to generate this white noise. It is a very, very important classical result, this spectral factorization, which was originally given by Wiener in the context of estimation and prediction. How to separate out given the module. If you remember, did we do this in network theory? If you are given a transfer function magnitude square, how do I find out what is the network? We will do. We will do that probably in the end of this course. How to pull out a realizable black box out of the magnitude square function. Okay. This completes our study on the discrete signals and discrete systems, both deterministic as well as random. What all we have not done in this till now is, or we are not going to do, is the black box also is a random black box. Because we have gone up to a generalization where the signal is a random, but the black box is still deterministic. How do I handle it if the black box is also a random? And this is also a real world problem, it is not that some hypothetical problem, because quite often that this black box corresponds to some systems which are unpredictable, in which case I will have to model it as a random black box. For example, you send a signal from one point to some other point, the signal goes through a medium in between. This medium goes on varying with respect to day-to-day atmospheric conditions, weather conditions, and so many parameters. So it becomes a random propagation. In which case, how do we model this? How do we handle such problems? Is the next step. I am not going to cover it in this course, but it is a real world problem. We study this called fading channels in communication. But quite often we assume that this signal to be, this black box has to be a completely deterministic black box, because but in real world it never deterministic, right? You take a mechanical system and you model the mechanical system. Hopefully mechanical system is fixed, but the mechanical system is never fixed, right? Because there is a friction there. Some oil is not sufficient, so friction has increased. So as a result of that, black box properties will change. Something or other will happen, the wear and tear of the system. All this will result in transfer function being a undeterministic. Hopefully that the variation with respect to mean value, the random part of it, is very small compared to the mean value. So we may say that hand waving that this is almost a deterministic system. But quite often what happens is the failures of the system only because of the small amount of undeterministic component, which is a random component. So nowadays everybody is worried about how to analyze a aircraft or any expensive equipment in terms of how does it behave under random conditions, and the system becomes random. So it is a real world problem. It is no more a theoretical problem, and we won't touch upon it, but you must keep in mind that this is a very important issue. Then we come back to continuous signals. And I think we are more at home with this. 101 we have covered this and how to handle continuous signals, x of t. By definition, x of t means for any given value of t lying between minus infinity to plus infinity, there is a well defined value for x of t. And we say that this value, this is a single valued function, meaning thereby for any given t, x is only one value, not multiple values. That means the function will never be like this. So for any t, there are so many values. So it is a single valued function, a continuous function, differentiable function, and so many mathematical descriptions of this function. We assume that this function exists, and also it has a finite amount of mean square value, it is not infinity. That means integral x square dt is less than infinity. we only deal with such signals, and we like to study such signals, characterization of the signal, which we already done in 101 and 102. And we also would like to know how the system behaves when it is inputted to a continuous black box with a equivalent of Hn, which we call as the impulse response, right. So, if we have a box here, if xt is given, you get yt, and this black box is represented by what? Impulse response, ht. And ht by definition is yt when xt is u0t. By definition. And we also studied that yt is equal to xt convolved with ht when the system is linear and time invariant. This we did in 101 and 102. I have now used descriptors called linear, and I use the word descriptor called time invariant. But all systems don't fall under this category. Quite often, most systems are nonlinear. Only we try to simplify the behavior of the system by modeling it as a linear system, because it is easier for us to analyze. But very often, the second order effects of the system has to be studied by modeling it as a nonlinear system. So, how do we analyze nonlinear systems? If it is NL, how do we analyze? If it is not TI, how do we analyze? Time varying. Because it is quite possible that the black box contains some elements which change with respect to temperature, and if temperature changes, the value of the resistor will change. So, if the value of resistor changes, the transfer function will change, or impulse response will change. So, the system may be time varying system. Many systems fall under this category of time variance, but again we try to model them as time invariant, saying that these variations are negligible and so on and so forth. But there may be systems which are intentionally made time vary for some advantages. If you have such a system of time varying system, how to analyze it? I will touch upon this topic and this topic in this course. It is a very complicated subject about study of the nonlinear systems, study of the time varying systems, but I will touch upon how to deal with these systems in a first simplified manner, but as a first order. Because I don't want you to go back and say that all systems are linear time invariant. No. Most systems are nonlinear, most systems are time varying. Only thing we try to model them as this because of this beautiful relationship that the input output is a correlation function, convolution function. So, we will pursue this building upon the whatever we have learnt in 101 and 102.